Recording has started, and I'm going to direct you to practice quiz and start with part A. You can go to part B as well. Okay, so number 1, A and B on the practice quiz, please. All right, anybody still need more time on 1A or B? Let's look at this first one. So y prime. The derivative of ln of x is 1 over x. So this one is also 1 over x. And then there's a penalty factor for the base not being e. And so it's 1 over x ln 3. When there's a denominator, the penalty factor goes into the denominator. Now, by the way, if this had been y equals ln x with unwritten base of e, then y prime 1 over x, if you included the penalty factor, that would have been fine, because e to what power is e? That's just 1. And so this general rule with the penalty factor can always be applied, but you only need to apply it when the base is not e. All right, in part B, y prime, the derivative of e to the x is e to the x. So this becomes similar. It stays the same. Oops. And then we have to chain on the derivative of the u function, because it's not just 4 to the x, it's 4 to a function of x. And so that's going to be 6x minus 7. It's chained on at the end of that. All right, give me a little feedback. How do you feel about 1A and B?
I have a question.
Yes.
Don't you have to tag on ln of 4?
Oh, thank you very much. The base wasn't e, so we had to have a penalty factor. So we got to throw in the ln of 4. So this had the du dx and the ln of 4. Very good. Thank you, Bianca. All right, so give me feedback now. And if there's particular parts, like if you're forgetting the ln4 or the du dx is the hard part or something like that, let me know. Okay, and alright, go to C. So they start to get a little bit more involved now. So those are the basics of an exponential function and a log function. And now extra complications. Starting, let's just do C. Anybody need more time with C? Alright, the outermost function is something squared. So we have to look at that. So for the chain rule, it's 2 times that thing to the first power. And I'm not going to write to the first power. So I could put brackets around it all to the first. And then times the derivative of everything else. So all we've really taken care of is the outermost function. And then when we take the derivative of everything else, so let me put some space here. So this is y prime. Derivative of log base 5, the derivative of ln of x is the foundation, and that's 1 over x. So this just becomes 1 over this. So I'm just going to put this whole thing down here. But it was supposed to have base e, penalty factor, when there's a denominator, it goes down in the denominator. And then there's the du dx, the inner function. When you take its derivative, I get negative 3x squared. The du dx does not go in the denominator. It just goes as separate to the side, but then it'll wind up coming up with the numerator, like this. And when I clean that all up, this negative 3 and this 2 would be negative 6x squared. Okay, we get this. So, give me feedback on this. Okay. So quite mixed feedback. Let's go to the next one. So that one was probably the most intricate. So many things involved there. Let's do the next one. Let me go ahead and renumber it. Okay, anybody need more time? So, y prime, it's a product rule. First times the derivative of the second plus the second times the derivative of the first. E to any power is e to that power. This doesn't have a penalty factor because it has the correct base of e. But then you have du dx, which is a 2. So y prime is e to the 2x over x plus 2e to the 2x ln x. That's how we could state our final answer. And give me feedback on this one. Okay, where did the 2 come from? Let's come back. That 2 was the derivative when you took the derivative of e to the 2x. The derivative of e to the u is e to the u du dx. So we have to take the derivative of the 2x with respect to x. Getting that 2 right there. Glad you're asking what you need clarification with. And, alright, let's go to number 3. Now, if you finish number 3 and have a little extra time, try doing it again in a different way. All right, anybody need more time? All right, y prime is equal to. Now, I'm going to do it 2 different ways. The first way is going to be the harder way. Log base 3 of some function. The derivative of log base 3 of some function, which is 5 to the t, is the same as the derivative of ln of u, which is 1 over u. So it's 1 over 5 to the t. Now the base was supposed to be e, but it wasn't, so we have a penalty factor, ln 3. Alright, so the derivative of log base 3 of u is 1 over u, and then we have to do the derivative of the internal after that. And then y prime is equal to 1 over 5 to the t ln 3. When I take the derivative of if it was e to the t, it'd be just e to the t again. So the derivative of 5 to the t is 5 to the t. And then a penalty factor for not having the correct base, ln 5. Now, what happens is cancellation. And I get ln 5 over ln 3. Now, we didn't have to do it this complicated. If we'd used a property of logarithms, we could have wrote the original problem this way. This t comes out front. It's property 3 of logarithms. Alright, now we realize this log base 3 of 5 is just a constant, like the number 7. And then dy dt of 7t would just be 7, or the derivative of this is just the constant. Now, we could leave our answer like this, but most calculators don't have log base 3. So I might change my answer to either log base 10 or log base e. If I use log base e, the ln, it's the change of base formula, ln 5 over ln 3, and I could get my answer to look exactly like that if I did it this alternate way. Alright, feedback on this. And if you understood both ways, if you have a preference, how are you feeling about this?
So, Mr. Shankin, so log base 3 of 5 would be a constant then?
That's right. There's no variables in it. As long as there's no variables in it, it's a constant. Yep. So let's go to number 4. And let's this last one is supposed to be part E. Okay, let me stop you now. I'm going to do part of it and then give you a little bit more time. So, if this was me doing this problem, I would tend to ignore the questions and play around with the function. And what I typically do is I describe my input and output variables. This is time. It doesn't say what units it is. H is height. It doesn't say what units that's in either. And I might just play around with some values in here. Time usually starts at 0. And when it's 1, I get 3 plus 2 is 5, minus 1 is 4. When it's 2, I get negative 4 and positive 4 canceling each other out, back to 3. When it's 3, negative 9 and positive 9, back to 0. And I would then conclude, the ball went up, and then when it hit after 3, maybe this is seconds. Well, it's for ease, I might call it seconds in feet or something like this. After 3 seconds, it's back to 0 feet, and so then I bet the equation doesn't apply anymore after that. And then, so I can get this answer by just making a table. I can also, when does the ball hit the ground, I can do it more abstractly. H is the height. When it hits the ground, it must be that the H is 0. So in an abstract way, I would take this as 0 and plug it in for the H into that equation. And then I like to have everything positive. I'm more comfortable. So I'd factor out a negative. I could divide both sides by -1. That negative won't matter in the solutions yet. T and T, plus and minus. I want the larger one negative, 3 and 1. And so at t equals negative 1 and at t is equal to 3, you're going to have h is 0. Now negative 1 is before we started, so that doesn't make sense. We throw that solution out. And so we'd say, this happens when t is equal to 3. But that's the same thing my little table is showing me. So I'd get some intuition of what's going on. I could also solve this equation. And I got this. The ball's initially thrown from what height? Well, when it's initially thrown, what's the time? It's at time 0. So I just plug in 0, and then the h must be, these two things 0 out, so that's 3. It was initially thrown from height of 3. If you recall from this kind of analysis before, the constant number is the initial height. The number in front of the t is the initial velocity. So that if we didn't have this first term, the negative t squared term, this thing would just keep getting 2 feet higher every second. And then it's this negative t squared that has to do with gravity pulling it back down. Now, what's the max height of the ball? Alright, so now that I've done a fair amount of this, let me give you another minute or so to see if you can get further than you've gotten so far, and see if you can get to C, D, and E as well. I'll give you a minute. And I have a fan going to keep me a little cool here. Is that disturbing the quality of the sound of my voice? Or is that okay?
I can hear you fine.
Okay, thank you. All right, anybody need more time? So, what's the max height of the ball? We can look here, and it looks like it's 4. But what are other ways that we could figure out the max height of the ball? One of the ways to figure out the max height of the ball is if we skipped C and went to D. What is the velocity of the ball at its max height? It appears to be a maximum height of 4 from the little table, but at its max height it's dropping at 0 feet. So this would be 0. The velocity of the ball at its max height must be 0. Set up an equation containing the derivative, which must be true when the ball reaches its maximum height. So the derivative, dh dt, is negative 2t plus 2. Now, at its max height, the derivative, or the velocity, is 0. We solve this for t. T is 1. So it must be that it gets to its max height at t equal 1. So this thing in the table must indeed be the maximum height. The max height must be 4. And so what is the max height of the ball? It's h equal 4 if we just delayed it and just did these two first. You could have also done c by graphing this function. If I graph this, I get a downward parabola because a is negative, and the vertex of a parabola is x, or in this case t, is negative b over 2a, negative 2 over 2 times negative 1, and that gives you negative 2 over negative 2, which is 1, which also tells you that this is a downward parabola where its vertex is when t is 1, so then its maximum height, you just plug in t equal 1 and get h equal 4. So you can do this, you can answer this question in a non-calculus way by just vertex of a parabola, or the calculus way, which is velocity, which is the derivative of the position function, and set that to 0. All right. Can you give me feedback on this? Feedback could be something like, I needed a little help getting going at times, or needed help on this or this, but, or, however it was. Pan is good, thank you. All right, thanks for the feedback, Amanda. Okay. All right, so let's go to questions. Questions on homework. Number 57. Following table shows the time of useful consciousness at various altitudes in the situation where a pressurized airplane suddenly loses pressure. The change in pressure drastically reduces available oxygen and hypoxia sets in. The upper value at each time interval is roughly t equals 10 times 2, so on, where t is measured in time and a is the altitude over 22,000 in thousands of feet. Okay, and so it gives a table, times of useful consciousness. A Learjet flying at 38,000 feet, A equals 16, suddenly loses pressure when the seal in the window fails. According to this model, how long do the pilot and passengers have to deploy oxygen masks before they become incapacitated? Alright, so this is 38,000, and do we use this? Alright, 38,000 should be giving me somewhere between 15 and 60 seconds, according to the table. But to get a precise number, we're going to just plug it into this formula right over here. So, the formula, A is altitude, and T is the time. And we're going to find, so on A, it's asking us to find T when A is equal to 16. So all I'm going to do on this one is take this formula and plug 16 into it, and then punch it out of my calculator. What is the average rate of change of T with respect to A over the interval 24,000 to 30,000 feet? Alright, so when it says average rate of change of T, they're talking about the derivative. So we're going to have to find dt dA. We take that derivative. Then it's average change. Oh, okay. Now this is actually C, the instantaneous rate of change. We do that, and then we plug in for 30,000 feet, and 30,000 is 8,000 more than 20,000. So this is A equals 8. So then we would we'd find dA, and we evaluate it at A equals 8. That's for C. And for B, find the average rate of change of T with respect to A on this interval. We might make a little A and T chart. And when A is, when we have 24,000 feet, that means A is 2. When we have 30,000 feet, that means A is 8. And then you plug in 2 and 8 into here and get your outputs, and then you're just going to find the slope of the line that goes between these 2 points, and that will get you part B right here. All right, so yes.
I don't understand how you get A.
How you get little a?
Yes.
Okay. A is the altitude over 22,000 in thousands of feet. So when you're at 22,000 feet, little a is 0. At 23,000 feet, A is 1. At 24,000 feet, A is 2, and so on. Is that clear, Kylie?
Not quite, but I'll see if I can figure it out.
It's kind of complex when it says in thousands of feet. All right. So, for instance, that's why I knew that when it's 30,000 feet, that's 8,000 feet more than 22,000. So if A is 0 at 22,000, then A would have to be 8 at 30,000, because it's 8,000 feet more than 22,000.
So A is like saying 1,000 more than 22,000 feet?
Yeah, how many more than 22,000, but in thousands? Yes. How many thousands of feet it is more than 22,000. Okay. So that's as much as I want to do on 57. And let's see, any other problems anybody wants me to look at? All right, if no other questions, we can go right into the new section. Maxima and Minima. Alright, and topic 1, just to remind me, there is a section that we are skipping, and it is I believe it's 3.10, derivatives of the inverse trig functions. Alright, so when you take the derivative of any trig function, you always get another trig function. It always happens that way. And no matter whether you're taking the derivative of secant or tangent or whatever, take a derivative of a trig function, you get another trig function. So it would seem to me to be reasonable to think that if you took the derivative of an inverse trig function, that you probably would get an inverse trig function, or at least a trig function or something. But what is surprising is you don't get any trig functions in your result. If you do a derivative of a inverse trig function, you get an algebraic function. This thing on the right doesn't have sine or cosine or anything like this. All it has is some algebraic manipulations. Squaring, subtracting, square rooting, reciprocating. And the derivatives of all of the inverse trig functions don't give you any trig functions at all. They just give you algebraic functions like this. Alright, now, technically speaking, I am supposed to cover this section. There's like state mandated requirements that you're supposed to cover all these different topics. What I have found in my many years of experience teaching calculus is students, if I go through more than one section a day, students have to wind up abandoning understanding why and just kind of memorize procedures, and it's not very useful for students. And so I limit myself and I exclude certain sections. And derivatives of inverse trig functions in section 3.10 is one of those sections that I chose to omit. But there are going to be problems in future homework assignments where you're going to have something like this, the derivative of the inverse sine, and you're going to have to get it. And so if you had a physical copy of the textbook, I bet that many of you, perhaps most of you, don't have a physical copy, you're just using it online. But in any physical copy of a calculus textbook, at the very back of the book, sometimes also at the very front of the book, they put a whole bunch of formulas, the standard formulas. And this textbook has the listing of the derivatives of all the different functions, the basic functions that you need, including the inverse trig functions. And so you can easily just Google that, derivatives of inverse trig functions, or print out, I would suggest, because you have access to, for the textbook, you have access to the online version of the textbook. You could go to the appendix and print out those basic formulas, but you want to have some basic formulas to refer to. And so this one is, and it's one of the reasons why I could skip this section, is there's just some easy rules that you could just look up when you need them. like the derivative of the inverse tangent is this. And the derivative of our inverse sine is this. Derivative of inverse tangent is kind of a little bit simpler, 1 over 1 plus x squared, and so on. So you want to have access to some of these basic formulas for the derivatives of inverse trig functions. So print some of those out, have them available. You are going to need them at some point in the future and in future calculus classes. All right. Well, let's go into 4.1 maxima and minima. And the first thing is this. All right. So number 2. And for this, I need you to work with your group. So be also in the chat and state the x-coordinate of each extrema. State whether it's a local max or min or an absolute max or min. Now those definitions are pretty intuitive. The absolute max is the highest point on this whole graph, and the absolute min is the lowest point on the whole graph. But a local max or min is the highest point in some region, and or lowest point in some region. And so you want to follow the instructions on A, and then where you're really going to need to, this you can kind of do individually on A, but on B is where you're going to really need to consult. List the mathematical characteristics of an extreme value. So you're going to get a whole bunch of extreme values here. You're going to be listing them. And then you're thinking of, well, what are mathematical characteristics of extreme values? And I'll be calling on groups, and we'll kind of build up a list here of characteristics of extreme values. Okay, about 30 seconds more. Let's focus on the mathematical characteristics of extreme values. All right, let me have you stop. And I'll do part A. So this point up here is the, oops, I'll just put an X there. That's the, at P we have the absolute max. It's also a local max. In any local region right nearby it, it's the highest point, and it's the highest point for the whole region. And then the absolute min is over here at A. And then there's a local max, a local min, a local min. This one is nothing. This one is a local max. All right. Everybody clear on that? Any questions so far? All right. So now let's go to part B. List the mathematical characteristics of an extreme value. And I'm going to ask group 6. Mathematical characteristics.
I think we're gonna have to pass on that one. We still don't have an answer.
Okay, not sure? That's fine. Let's go to group 4. Mathematical characteristics. Extreme value.
We came up with that a mathematical characteristic of extreme values is that they don't have derivatives at those points.
Say that again.
A mathematical characteristic of extreme values is that they don't have derivatives at those points.
They don't have derivatives. Is that right?
Yes.
They do not have derivatives. All right. Of all the points that we see here, where do you not have a derivative?
At the extreme points. Let me get on it.
All these, how about, what's the derivative way up here on P? And at Q and at R. What's the value of the derivative at each one of those points?
I'm assuming they're probably constant values, so 0.
That is correct. The tangent line at each of those points is 0. So if we, let's go back here to my eraser. If I was putting my tangent lines, horizontal tangent lines, here actually is another horizontal tangent line, right here. But, oh, that's significant, very significant, is that mathematical characteristics of extreme values is they tend to occur, not always, when the derivative on f prime of x is 0. When the horizontal, when the tangent line is 0, that's when we tend to see an extreme value. All right, now, were there extreme values that it was not the case, though, that the derivative was 0? Anybody?
At point S.
At point S. And what's happening at point S?
That's a cusp point, so it's not differentiable.
That's right. Tend to occur when this or more rarely, when f prime of x does not exist. When f prime doesn't exist, because why does it f prime not exist? Because if you approach this point from the left, your tangent line looks like this. If you approach from the right, your tangent line looks like this. But when you approach from the left and from the right, you have to get the same tangent line for that limit to exist. So that's why it has no derivative at s. All right, now, is there any other points that were extreme values that were not either one of these two cases, where the derivative was 0 or where the derivative does not exist?
Point B?
Point B, that is correct. And what's happening at point B? That's what we... Yes?
When the derivative doesn't exist on the right side, that means there's no limit.
Ah, okay. And we'd say only the derivative from the left exists there. We can also simplify that even further and just say the only other case would be at endpoints. Okay? So, local extrema or absolute extrema, doesn't matter, either one of those, they're only going to occur either when the derivative is 0, when the derivative does not exist, or at an endpoint of an interval. Those are the only ways you can find extreme values. Now, we're going to simplify and make life easy, is that we're only going to consider extrema on open intervals. Now, on open intervals, let me show you. Suppose we had something that looked like this. Now, I'm going to fill this one in, but I'm not going to fill that one in. Okay. Now, where does the max, so if this was my xy axis, and this was directly above A, and this is directly above B. All right. What's my absolute max? Well, it's at x equals b. What's my absolute min? Can anybody tell me what is the absolute min? Where does that occur on this function?
When x is a plus 1.
Right. You would have to add something to a. Because if you didn't add something to a, if you just said the absolute min occurs when x is a, well, a is not part of the interval. It's this interval includes the endpoint b, but does not include the endpoint a. So you'd have to add something to a. But if you add 1, somebody could say, well, hold it. What about if we added 0.1? Wouldn't we be even lower? Yep. And what if we added 0.001? We'd be even lower. And is there a lowest point in the interval? The answer is none. There is no lowest point. You have to add something to a, but what's the smallest amount you could add to a? There is no smallest amount. So you just have to say that this doesn't have an absolute min. It has an absolute max, but doesn't have an absolute min. All right. So it doesn't even have a local min. There's no point in this whole curve that is the lowest point within a region. even a really small region. Okay, now when we talk about a little region, one way you can visualize that is like we could say that, let me draw a little circle there. Is there a highest point inside that circle, but I can't take it on the edge of the circle? You'd say no. Is there a highest point within this circle, but I can't take an edge point of the circle? Yes, it would be where that green line is, right up there. All right. So this point here has no, this interval has no local mins nor any absolute mins. And so what we're going to do is we're going to only take extreme values on open intervals. And so if we make that only on open intervals, we would be doing something like this. Make a big circle here and make a big circle here instead of closed circles. And then you can't consider those as absolute mins or local maxes. And so then extreme values on open intervals only occur at one of these two situations, where the derivative is 0 or where the derivative does not exist.
I have a question.
Yes.
What if in the case of the graph with AB, what if it was a removable discontinuity?
All right. We're also, that's a very good point, Bjarke. We are also going to focus on continuous functions. So where there's no discontinuities whatsoever. When you have discontinuities, you can have all kinds of exceptions like this. But we'll be looking, the theorems we'll be looking in this section is for functions that are continuous over a certain interval, how do I find the highest point and the lowest point? So not only will we remove endpoints out of the consideration by taking only open intervals, but then we will remove things like removable discontinuities because we'll just require it to be continuous. Okay? And now there will be times when we do have endpoints as part of an interval. And when we do, they could be an absolute max or absolute min, but we'll see the main theorems are going to take those out and just say that on an open interval, this is. So let me give you that one main theorem, and then we'll take a break. And so let me go to the camera. Definition. A critical point on, now notice how important this is, on an open interval of a function f is either one of two cases. A stationary point, where f prime of x is 0, or b, a singular point, where f prime of x does not exist. Okay, so we only get these two cases, and this is an important definition for us of what a critical point is. And we'll come back after a break and we'll see how this relates to extreme values. So we'll start again. At 12:51. Okay, back to it. Excuse me. All right, let's start again. Put another light on here. All right. So then we have a theorem. Extreme values now, extreme values are either local or absolute maxes or minimums. Extreme values on an open interval. This is so that we don't have to consider endpoints of a continuous function so that way we don't have to consider what Bianca brought up, like what about a whole discontinuity or something like this, of a continuous function are always critical points. So let's look this over carefully. To be an extreme value on an open interval of a continuous function, you're always a critical point. And a critical point is one of these two cases. You're either where the derivative is zero, and the reason why they call that a stationary point is, let's suppose it was a stock price. And if the derivative was zero day after day after day, what does it mean? That means the price of the stock is staying stationary. It's $21 a share every day, so on as you move along. Stationary point. A singular point where the derivative doesn't exist, as we saw that like with the cusp point. Okay. Now, I am going to go back to the picture we were looking at, and I'm going to be making a logical error as I deduce this, and see if you can figure out what my logical error is, and then I will give you a moment to discuss this in your groups, and then I'll pick on a group. And so let's go back to this diagram, and let me use my eraser. Okay, so you try to figure out what is the logical mistake I'm making. And I'm going to say that on this picture, each of these critical points, now imagine that these are open circles, so it's an open interval, and it's a continuous function. So if we just imagine that those are open circles instead of filled in circles at the end, then we meet all the conditions. Now, critical points are here, here. Each one of these critical points is an extreme value. That's what the theorem's saying. Every single one of these critical points is an extreme value. And I've just made a logical mistake. See if you can discuss that in your group and figure out what it is. I'll call on a group in a minute. I'm saying each one of these critical points must be an extreme value. I'm going to give you a minute. Has everybody had enough time? Let me ask group 3. Do you see my logical error?
We think that it's the point S.
And the point S is at a critical point.
No.
And let's flip over to here. Critical point is either, and one of the options is where the derivative does not exist. So yeah, it is a critical point. It's a critical point, and it's also an extreme value. It's a local minimum. So the point S is not the logical error. Good guess, but that's not it though. There's something else. Let me ask group 3. No, that was group 3. Group 2, do you have anything on that?
Jaden's supposed to be our spokesperson, but I don't know if he's. No one was commenting in our group because I don't think anyone's there. You can't assume that both the cases, because one, it could be either a point where it's not differentiable, or it could be a point that identifies a max or a min, but maybe not both.
That's missing it a little bit. Okay, the error that I'm making is, let's go back and look at this theorem. It says that if you're an extreme value, if it's an extreme value, that implies that you're a critical point. And the way that I stated it is I reversed it around. I stated it this way. If we're a critical point, then we must be an extreme value. But there's an error in that thinking. And the error shows up if you can look at this portion of the graph, right here, and let me go to green. The tangent line is horizontal right here. Now, the tangent line is horizontal at that point. So, if we go to here, is it a critical point? Yes, because the derivative is equal to 0. If it's a critical point, does it necessarily mean that that's an extreme value? Well, that's not the highest point in any region, nor is it the lowest point in any region. To be a critical point is a possible, not necessarily an extreme value. To be a critical point, it's a possible extreme value. If it's an extreme value, it's always a critical point. Every extreme value on an open interval of a continuous function is a critical point. But critical points is not the same as being an extreme. That doesn't mean that these two are the same thing. Being a critical point, there are exceptions, and here's one of them, where the derivative was 0 for an instant, and then it changed its tendency. Instead of this curve dropping down, it then changed and started going up again. Yes, somebody wants to comment?
Oh, I'm sorry. No, I have just a question. So, would you, in order to determine if you had a critical point for certain, would you have to look at the values before and after to see if they're like switching from increasing to decreasing or vice versa?
That's right. That's one of the ways to verify it. Or you might just look at the picture on the graph. That could verify it, but that's, if you didn't have a picture on a graph, you might use that kind of language, switching from increasing to decreasing. If that happens right then you're, which is the case on all the other ones. So over here, the stock price is going up, and then it's going down, and it's switching from increasing to decreasing right at that critical point. And that's what happens at most critical points. It switches from increasing to decreasing, or from decreasing to increasing. But once in a while, that doesn't happen. And if that's the case, then even though it's a critical point, it's not an extreme value. It's probably an extreme value in most cases, but not necessarily. There are exceptions. All right. So, this, when you have an implication, if this, then this, it's very important that which direction you're going in the implication. And we just saw in this one that extreme value implies that we're always a critical point, but always a critical point is not always an extreme value. All right. Give me a little feedback on this. Are you confused on this? Or is it making sense? Do I need to explain more, or should I move on to a different topic with this? Alright, we might review it a little bit more, but I think mostly we can move on from this. Alright. Let me print this screen. Let's do an example problem. Example 1. Find the absolute max and absolute minimum of f of x equals 1/8 x cubed minus 1/2 x on a closed interval from -1 to 3. All right. And before we do this, let's notice that we've been talking about, with the definition of a critical point and that theorem about extreme values always being critical points, that was assuming we were on open intervals. Now we've changed and we're on a closed interval. And there's another theorem that applies for closed intervals. Theorem. If function f is continuous, on a closed interval a to b of the x-axis, then f has an absolute max and absolute min on the interval, closed interval a to b. So the idea is, if you're going from A to B, if it's closed, meaning you have filled in endpoints, you've got to have a highest point on the interval and a lowest point on the interval. And it makes intuitive sense on that. On open intervals, like if this did not include the left endpoint A, we'd say we don't have a lowest point on this curve. But on closed, we absolutely have to. All right, so we're guaranteed that we're going to get that there's an absolute max and an absolute min in any closed interval, and now it asks you to find it. So, let me print this. Let me erase this theorem. And before I start, let me make a little table. I can tell that, you see, because the graph of this thing from -1 to 3, I'm just carrying what's happening to this function in this interval between -1 and 3. And it's got to have a highest point, it's got to have a lowest point. And I know I'm going to have to check the endpoints. always we want to check the endpoint. The highest or lowest point could be an endpoint. We'll plug in -1 into this function. I'm going to get -1/8 plus 1/2. So that's going to be 4/8 minus 1/8. It's going to give me 3/8. When I plug in 3, I'm going to get -3/2, and then plus 27/8. 8 goes, well, I'll just punch that out of my calculator. I get 1.875, and in decimal, 3 divided by 8 is 0.375. All right. Now, if this was all the information I had, I would conclude the absolute max occurs right here on the right edge. Because if I go up 1, 2, if I go up 1.875, that's the highest point. And if I go up 0.375, that looks like the lowest point. So if this was the only information I had from this table, I would say, here's the absolute min, here's the absolute max. But the function could possibly rise up and then come back down. That might not be the absolute max here. It could be happening somewhere else. How do I find out if there's some other points I need to check in here? And how do I do that? So take a moment. Consult in your group, and then I'm going to call in the group in a minute, and you tell me the strategy you would use, how I'd go about getting more points. Excuse me. All right, 10 seconds more. All right, group 4. What strategy would I use? How would I find out more points to put in here?
We're still consulting, but we figured that you would either graph or try and find all the output values between -1 and 3.
So you could just like put in more numbers in the table, or put this into like a Wolfram Alpha and graph it.
Yes.
Those would both work. But let's suppose you weren't allowed to use either one of those. Let's say you can't use a graphing calculator and you want to use some calculus method that would
By derivative then?
Pardon?
By finding the zeros of the derivative then?
Now, so you'd take the derivative to start with, and it would be 3/8 x squared minus 1/2. And then you said find the zeros of the derivative?
Yes.
set it equal to 0. Now, why are we doing this, Sally?
To find the biggest value, I would assume, but
All right, when you're setting the derivative equal to 0, what you're doing is you're saying, I'm finding the points, like suppose this curve did something like this. This point right here would be where the derivative was 0, and that would be the highest point. Or, if it went up and down and up, it would find all such points where the derivative is 0. Replacing this f prime of x with 0 is the equivalent of saying, let's find the x values that correspond with these things happening, where the tangent line is horizontal. And those would be the points, the only other points I need to look at. If you went and put like all the points in between here, like 0, 1, 2, and 3, you still might not get your absolute max, absolute min, because it might be happening at 1.37 or something like this. So this calculus method will zoom us directly into the points that we were looking at. So I'm going to add 1/2 to both sides. I'm going to multiply both sides by 3/8, or by 8/3. And then this is going to be 4/3 is equal to x squared. I'm going to take the square root of both sides. You have to put plus or minus. Square root of 4 over the square root of 3. Or plus or minus 2 over the square root of 3. You can rationalize that denominator, but you can also just leave it like that. Alright. These are the only values that we're really interested in. Now, 2 divided by the square root of 3. This is approximately equal. Let me punch that out on my calculator. It is plus or minus 1.1547. Now, do I want to put both of these into this table? Well, if I put the positive 1 in, that for sure is in between this interval of -1 and +3. But the negative of this is to the left of -1. It's outside of the region of interest, so I don't even bother with that one. You only take the, now these are what we call the critical points. Critical points are hugely points of interest for us. It's where something really important happens. If the function changes from increasing to decreasing or vice versa, it happens at a critical point. So we plug only the positive 1 in. Is not in the interval -1 to 3. Okay. And we find out what the f value. Don't plug this into f prime. Plug this back into f because we're making a table of f. So I have the positive 1. And that, and I'm going to take that cubed divided by 8 minus that divided by 2. And I get negative 0.3849. So, the only point that was significant, besides the endpoints, turned out to be a little more than 1. So we had here, we had here, a little bit more than 1, it was down here. This was my picture of what's happening. And so I can see that my absolute max that's the highest of these, it's the largest of these 3 values. The absolute min, take the smallest of these 3 values. And this point right here was neither the highest point nor the lowest point. It was in between, so we don't even mention that. All right, let me review, because there was kind of a fair amount going on here. If you're trying to find the absolute max or and min on a closed interval, we know that that can be done because of the theorem. We know we have to check the endpoints, and the only other ones in between that are candidates for absolute max or min are the critical points. So we take the derivative, set it equal to 0. Now, another thing can happen, and I have to mention it here, is sometimes when you take the derivative, you'll get, like for instance, if your function was the square root of x, what happens when you take its derivative? Now, this is the same as this. Alright, now if you set the derivative equal to 0, you replace this side with 0, you're going to get no solution. Because the only way a fraction can be 0 is if the numerator, the top part of the fraction, is 0. And the top part of this fraction is always 1, so you'll get no solution. But if x itself is 0, it causes the fraction to not exist. So the derivative won't exist when x is equal to 0. And that also is a critical point. Remember, there are 2 types of critical points. One where the derivative is 0, and the other is when the derivative does not exist. And that one where the derivative does not exist, we'd have to then check that one and put that one into our table. So we have to look on this one, the derivative existed everywhere. But some of them, when a denominator could become 0, then we have to watch for those cases, and we make sure we check on those as well. All right, give me a little bit of feedback. How's it going with this? Is this all understandable? So let's look at another example. Oh, let me print screen on this first. I started to erase. We'll get what we get here. Example 2. Find all absolute extreme values of f of x is x to the fourth minus 4x cubed plus 4x squared on the closed interval -1 to 3. Alright, so I'm going to give you a minute to get ahead of me on this, and then I'll start working. Now it's just coincidence it has the same closed interval values as the other one. Okay, so I'm going to make a little table, x, f of x, and for sure what's got to go on there is the endpoints. Those could be the absolute max or absolute min. But what we also must include is any critical points that lie between -1 and 3. So I must take the derivative and then set the derivative equal to 0. When I set the derivative equal to 0, what that's doing is between -1 and 3, I don't know what this function is doing. I'm only interested in it in between these intervals. But suppose it's doing all kinds of crazy stuff in there. when you set the derivative equal to 0 and then solve for x, it finds the x coordinates of those points. Now it might also find an x coordinate of something that's outside of that interval, and we're going to say, oh, I don't care about that. I just want the ones that are between -1 and 3. All right. So I'm going to have to solve this equation. There's 4x common. Factor it out. And then its further factors. Both of them have to be minus, to multiply to be a positive, 2 and 1, to give the correct middle term. So the three solutions are x equals 0, x equals 2, and x equals 1. These are all critical points. Now you also have to be aware of, we haven't seen it yet, but you also have to be aware of if you came with a denominator, with the variable in the denominator, the value of the variable that caused the denominator to 0 would also be considered a critical point, because then the derivative would not define that at that point. So these are the critical points. Are all of these in between -1 and 3? Yes, they are. So all of them have to go in here. And so this graph, let me erase it because it's kind of deceiving. It's not the real graph. It's just a possible graph. So then I just plug all these into this function up here, and I can use my graphing calculator. There's shortcut ways to do this kind of stuff quickly with a graphing calculator or on the computer. Some programs allow you to make tables. So when x is -1, I get 9. When it's 0, I get 0. When it's 1, I get 1. It's 2, I get 0. It's 3, I get 9. So, all I really need to do is pick the smallest output. There's two that are tied to for the smallest. So the absolute min now the critical points. You might be wondering, can I just say x equals 0 is a critical point? Because when x equals 0, y is also 0 if you plugged it 0 into here. And so you might say 0, 0 is a whole point. But there's no real convention on that. Sometimes we just give the x coordinates and say those are the critical points. Sometimes we say the point 0, 0 is the critical point. Technically, you know, if you use the word point here, you'd expect it to be a point there, but sometimes they just tell you the x coordinate of the critical points. So the absolute min, there's two of them, 0, 0, and 2, 0. And the absolute max, there's two that are tied, -1, 9, and 3, 9. And it might help to visualize what's happening here. And we're going to need to go up to a height of 9. Here's a height of 1. Here's a height of 9. -1, it's at 9. 0, 0. 1, 1. 2, 0. 3, 9. Looks like this curve is doing this. So, those are the two lowest points, those are the two highest points, and we got it. Any questions for this? Let's do just a let me see if we have time. Hang on a second. All right. We have time to just start a different problem. Example 3. Find all absolute extrema on the interval 0 to 27 for the function f of x is equal to 3x to the 2/3 minus x. Since we're running out of time, I'm going to just zip through this very quickly. I would make my table. Of course, I have to put my endpoints. And then I have to see what points in between I'm going to need to use. To figure out what points in between, I set my derivative, find my derivative. I'm going to get 2x to the -1/3 minus 1. Okay. Now, then I set this derivative equal to 0. Now, it's at this point many students will solve this equation and fail to realize that there is a value of x which causes this to not exist. Let me rewrite this. Like this. This and this mean the same thing. 1/3 means cube root, negative exponent means in the denominator. If you see this at this point, you can say if x equals 0, f prime of x does not exist. Thus, x equals 0 is a critical point. Now, in this particular case, 0 was also an endpoint, so we were going to get it on the table no matter what. But there'll be some situations where when you solve this one, it'll be some point in between, and you have to have that in this table. Okay, so that one, then the other one, we have to solve this. So I'm going to add 1 to both sides. I'm going to cross multiply. So this times this is equal to this times this. And I'm going to cube both sides. So 8 is a critical point. So then I'm going to plug in 0, and you get 3 times 0 minus 0, which is 0. Plug in 8. Cube root of 8 is 2. 2 squared is 4. 4 times 3 is 12. 12 minus 8 is 4. I plug in 27. 27 to the 2/3 turns out to be 9. 9 times 3 is 27. 27 minus 27 is 0. So, of these three, the absolute max occurs at 8, 4 as the highest output. Absolute min, there's 2 of them, 0, 0, and 27, 0. All right, so the homework is 4.1. The end of this week is going to be exam number 3. And if you look on our schedule, you will see that exam covers 1.3 and all that we did in chapter 3, 3.1 through 3.9. Then the schedule also mentions that you'll be starting through the review for your final exam. I'll be giving out a review set of problems to do to get ready for the final exam, and so you can start working on them at that point. And we'll stop here for today. Are there any questions?
I had a question about just, I guess, some intuition about when you do find a critical point because the derivative does not exist, or you like you were saying, if it's in the denominator and it's undefined, to determine if it's an asymptote versus a cusp point, would you plug it back into the original function to see what it does, or how would you determine that?
Okay, generally speaking, if you see the original function, look at the original function on this one. This one, that's going to be a cusp point because it doesn't have a 0 in it. There's no variable in the denominator. So there's no vertical asymptote for this one. And so 0 itself just winds up being a cusp point. If, let's say this was 3x to the negative 2/3, so it was in the denominator, then there's a vertical asymptote at x equals 0. Where there's a vertical asymptote of the function, that will also be the case that the derivative won't exist. When you take the derivative at the same value, it won't exist as well. So you can usually tell where the function has a vertical asymptote the derivative is not going to exist. If the function was defined there and there was no x in the denominator, then it's probably a cusp point. That's a general rule of thumb. Good question. Any other questions or comments? All right.
So,
yes.
if there are asymptotes in the equation, would that count as an absolute min or max? Like if you have a horizontal?
The vertical asymptote, yeah, it will never be an absolute min or absolute max. The function doesn't exist at that point. There's just a dotted line that goes straight up right there. So yeah, it gets excluded.
What about horizontal asymptotes?
Horizontal, that's different. You could have and you might have an absolute max or absolute min with those. That's right. Good point. Anything else? All right. I'll see you all tomorrow. And Bianca, you're staying after, right? You have a question we want to look at?
Yeah.
Okay.
Well, it's more so just help in general with 3.9.
3.9, okay. Anybody else who wants to look at what's going on with 3.9 can feel free to observe or participate. Should we look at a specific problem in 3.9? Oh, let me make sure.
I don't really have a specific problem in mind. It's just more so just understanding.
Okay. Hang on just a second. Let me print this screen and put it in here. And then I can erase this board. All right.
Did you stop the recording?
Oh yeah. Let's stop the recording. Good idea.